Test.
That's what, yeah, that. My test practice are done. I said, screw it.
All right. I should just go home. Let you guys work things out yourselves.
Hell no.
Yeah.
Really, I finished the lecture, bro? Because I wasn't here. You can't go above 19.
At most 19 means 19 or less. Yes.
I have like 4 pieces left. Last part. So 3 of the data values fall into
True. So if you
I
catch
might need
all
some
the
of that
16s, what percentage have you caught so far? 16%.
I agree.
Then you caught all the 23s, 12 more percent. And you caught all the 30. You gotta add the percent. They're not all equally represented.
Okay.
Yeah. When you have just a list and you can count the individual things, then you divide by how many there are, you're done. Do you gonna know how many are in this
The test
list?
is on chapter 7 too. So then you add all the and then
That's the percentage.
we get the, I was thinking the percentage.
Sure, okay.
I left my practice test to do
Sure,
all
okay.
night.
Yeah.
To study for the test tomorrow.
Anybody need a copy of the practice test? Practice test. Same.
I have something to do with some rugby dinner because our church is going east. So it's our first campus. So we have a dinner for all the kids' church volunteers. And I'm like, those are like 6 to 9. And I'm not.
Everybody has a copy of the Z-score chart, right?
So literally.
Anybody need a Z-score chart?
Take her home.
Z-score charts, everybody has one of those?
Go to this dinner, come home, do homework, go to bed, wake up, do homework.
Okay,
Yeah.
okay.
Well, and I need to do chapter 6.
All right, guys, so we have a few things to finish up in chapter 7. We just got into something really weird last time. And you're all like, every day is something weird, Jeff? Yeah?
Quick question before we get move on. So when you've got something that has discrete data, like one of the questions homework had like number of people in the room attending the graduation ceremony, and if you were saying like the average number of people expected, which gives you like a mean and the standard deviation, the average number of people expected out of these 22 people or whatever, if it comes out to like 19 point something.
There you go. That's the answer.
But like if it's asking like how
Average. Average can be anything.
No, but it's not asking the average, though. It's asking the number of people expected to go.
Expected. Expected value.
Can you 19.7?
So it's not talking about... So, all right, you could look at that two different ways. But the expectation can be anything because it's an average. Period.
Does that kind of go well with an average like expected value?
Yes.
Like keep that in mind, am expected. Just bring
Yes,
that over.
I like it. Okay. So let me remind you guys of a couple things. We'll do an example, and then of course I got a little handout. And the handout goes over chapter 6 and 7, which is nice. You pretty much have to, because 7 is all about an adjustment to what we do in chapter 6. Chapter 7 adjusts things. So, my pot could look like anything. Right? And say this is bowling scores for some group of people. This is the bowling scores for the population of bowlers. Everybody's ever gone bowling. So a lot of people really sucked. So I'd be right there. I suck at bowling. My little brother took all the bowling ability. He's made money at tournaments and stuff. It's got like 12 different bowling balls depending on the lane conditions. I'm like, dude, I just picked the one my thumb fits in. So the population, is this normally distributed? Oh, hell no. But when I start taking samples and start plotting those, instead of individuals, I plot groups of people at a time. The picture becomes normal once I get above what magic number? Who remembers? No?
50?
I love it. High, lower, high. No, screw that shit. So once you get n equal to 30, or greater than 30, and greater than 30, we'll do what this book says. Then it becomes normal enough. And I really want this to make sense, because if I start taking groups of people, the most likely thing to happen is a mixture of everybody. The most likely thing to happen is the actual average of the population. That becomes the most likely thing to happen. So whatever the average really is, let's say the average is about right here, it stays in the same place in this picture. This is the mean of all the sample means. I really want this to make sense. Instead of saying, what's your bowling average? Bam. What's your bowling score? Bam. What's your bowling score? I take a group and then I plot them. That's the new picture. The new picture is all the possible groups of size 30. And it's now going to look more like this. So the mean stays exactly the same. Whatever the standard deviation was, the standard deviation of the sample means. And real quick, everybody looks at this wrong. This x bar is a subscript. This is not sigma divided by anything. This is sigma sub x bar. This is the standard deviation of the sample means. This is the mean of the sample means. You guys cool with that? So if I took a size 30 group from you guys, figured out your average, figured out your standard deviation, and kept going, this is the average of all those averages, and this would be the standard deviation of all the averages. That's going to be the old one, the one for individuals, divided by the square root of my sample size. Whatever that is. The bigger this gets, the tighter this gets. Because what happens to my standard deviation? It keeps getting smaller and smaller and smaller as n gets bigger and bigger and bigger. Yes, ma'am. Say again? That is a square root, yes. Sigma over the square root of n. Just to give you two languages that you can't interpret my writing in. Mathish and English. Okay. So, practically, now this took a while for me to talk about, like everything seems to, right? This idea is kind of deep and kind of interesting to feel out. But practically what happens in a problem, I just do all the same work. But to get a z-score, I don't use this thing, I don't use this. That's for individuals. If I'm talking about groups of people, I have to use this standard deviation instead. That's the only thing that changes. So let's try a problem out. Let me make one up real quick, and then I'll give you guys the handout that's got several problems on it. Do it over here.
Yeah.
That's it. All right. Just to make something up real quick. So the mean length of fish in some lake somewhere is 18 centimeters with a standard deviation of 4.15 centimeters. 18 centimeters. Little tiny fish. Everybody with me so far? And this is true for all fish. You see that? All fish in this whatever lake. We know that they're normally distributed. Why is that important to know? What am I allowed to use then to find probabilities? Z-score. Z-score chart. I like it. So you can always make a z-score, but you can only do something more with them in certain situations. So if I want a probability from a z-score, I currently have to know if it's normally distributed. I say it that way because you can do more with it later maybe, but so let's see. Part A, if I pick one fish, what's the probability that the fish I picked is longer than 20 centimeters? All right, take a minute and see if you can do that. I would normally say this is an old problem, but for us, nothing's that old in this class. This is a classic traditional z-score problem. This is one that you have to be able to do really well. You want to find these on the test and do them. Can somebody tell me what's the overall idea here? I give you an x score. What are you going to do with that x score? Make it into a z-score. And then you're going to look it up. Get the percentage. That's your classic, straight up z-score problem. They tell me it's normal. I'm taking one fish. Nothing to change. Any Vikings fans out there?
No.
No?
No.
None of my teams are still in there, so I don't give a shit.
Not either. It's okay. We didn't get the playoffs.
What's your team?
Huh?
What's your team?
Oh my God. Patriots? Hell no. Oh, you know better than that. No. Dolphins.
I always
Or
thought
Dolphins.
better than that.
A friend of mine years ago convinced me to be a Bears fan, many years ago, and it's been an unhappy time since.
Yeah. Back in the days of the fridge and Peyton and all that was easy.
Like 10 years ago, he's like, ever since then, it's like,
All right. Now you guys know this is what the picture should look like, right? 18, it goes in the middle, greater than 20, so I put 20 down and it's shaded in. Now the real reason I do this is you know already the answer should be less than 50%. You guys see that? At least I know the answer should be less than 50%. If I get something more than 50%, I made a mistake. Let me know this guy. I don't remember if I deleted the old stuff. So now I got to make a z-score out of this. So z equals what? What goes on the top?
X minus mu.
Yeah, x minus the mean, so 20 is 18.
4.15.
4.15, I like it.
0.48.
Sorry?
Where'd you get 18 from? Oh, let me see that. I saw it on
What do you get? I'm sorry? 0.48?
0.48.
And why do I take it to two places? Chart only goes two places. A lot of people make a mistake and they don't. What happens a lot? What did you say? 4819?
Yeah.
They'll do this and they'll circle it because that looks like 48.19%, don't it? That's the probability, Jeff. I'm done. Next problem. But that is a z-score. That's why you tell yourself, "What the hell did you just do?" I only have a z-score. Yes, sir.
One of the things I've been doing on the homework, and I have a question about. So it has on here like common values result from interpolation of like the 1.645 and stuff. For the other areas, if to be closer to what you're looking for between the two, should you average them and do like?
Yeah. I only make you average them if it really is exactly symmetric between the two.
But if it's not like
You could do interpolation, is what it's called, and you could do figure out what percent of the way between the two you should be, and then interpolate. We're not going to do that.
Well, like just often, I'll look at it and it's like 0.1 or 0.015 away, 0.015 away, or 0.017 away. Average the two, it's way closer to what it
True.
actually is.
Yeah, I'll accept either one.
Okay, cool.
Either the closest one or the middle. That's fine. I'm not going to make you always do a certain thing. And again, some of you guys might realize I make you take it to 4 places and all that when actually we're using a chart which is imperfect. But I'm trying to get you used to being careful with your numbers. I'm trying to let you use the chart to get used to how things are spread out. If you go into a field that uses statistics, what are you going to do? You're going to use technology to give you answers. But if you don't know what the hell goes into that, you can't explain what the hell you get, right? So here we're going to use this crazy chart because Jeff has a reason for that. You're going to do all this shit. In the real world, technology is going to get it exact. That's all nice for it, right? But at that point, you understand it better. You're able to interpret it better. That's my hope. All right. So what do I do next?
Look it up on the chart.
Yeah. So if I look up 0.48,
0.68.
Yeah.
6844. And so of course the real answer is 1 minus that.
Okay, it's coming back. It's coming back.
Yeah. It's in here.
This side or this side?
Say again.
What do you do, that side or this side?
What's the chart always tell me when I look a Z-score up? What's the chart when I look that Z-score up? What's it tell me? It tells me the area that is below. Always. That's how the chart is designed. So they didn't have to make it volume 1 of it or something in volume 2. We're the humans. We have to know when to turn that sucker around. I don't want down here. I want up there. You've got to do 1 minus. Some of you guys remember the shortcut. That's great. Saves you like 3 seconds. But, you know. How does everybody feel about this problem?
It's pretty simple.
What are the key things? I told you it was normal. If I don't tell you it's normal, I don't do a problem. I don't do this. I don't make a trick question where the answer is I can't do it. That would be so evil. If you just missed that and you did the whole problem, you're wasting time. I would never do that to you. Do you understand? So either I got to tell you it's normal, or I got to give you a situation where you're supposed to know it's normally distributed.
I give up on those.
All right. So everybody's cool with this?
Yes.
Yes, sir.
I had a question about the base. Is it is not supposed to be the Z-score? Is that what we did last time for the 18 and 20 hits for your graph?
Okay, you can put 0 there. You can put 0.48 there.
Does it matter?
What do you mean?
Does it matter?
If I have raw scores, I definitely put those down there.
Okay.
Yeah. You could put the Z-scores underneath, just to keep, especially if you have multiple ones. I might put the Z-scores underneath to keep track of where the areas are when I look them up. Yeah. Okay.
So we don't always put 0.
Say again?
We don't always put 0.
Of course not. What's the only time I only put 0 here is if I'm only working with...
If you're just working with...
What's the only thing that the mean is always 0? Z-scores. Am I working with Z-scores here?
No.
No, not yet. So what goes in the middle? The mean.
The mean.
Always. What's the mean of Z-scores? Always 0. But I'm not working with Z-score. I'm working with fish lengths. So what goes in the middle? 18, because that's the average fish length. Yes.
So 0.315, that would be the percentage of getting it one.
Yeah, this is the probability. So you can look at this several different ways. This is the probability that a fish picked at random is longer than 20 centimeters. Another way to look at this is 31.56% of all fish in that pond are greater than 20 centimeters. That's the connection. If 30% of everybody in this room likes to go fishing, what's the probability I pick somebody that likes to go fishing at random? 30%. They're the same thing. So I can interpret this as the percentage of things that do this or the probability that it does that, because that's what probability means on that basic level. Yeah. All right. So what about part B? Part B is going to relate to this weird shit here. Okay? Part B would say, now, the triggers to know when to change the standard deviation are, we take a sample and I ask you about the sample mean. When those two things happen, I know I have to change the standard deviation. Because what is the standard deviation good for? What's it work for? What's that standard deviation good for? It's good for individual fish. It's how far apart individual fish lengths are from the average on average. Okay, you guys with me? This is for individuals. That's why I used it here. Because how many fish did I pick? One, an individual fish. So I want to know how is that individual fish distributed amongst all the individual fish. What am I doing here? Taking a group of 11. I got to know how that group of 11, how every group of 11 is distributed. Do they use the same standard deviation? Hell no. So I don't like to teach this directly. I got to take you through the whole idea of it. But now you can say, oh, if I see a sample being taken and the question is about a sample mean, I've got to change the standard deviation. Because that's the one that's good for individual fish. I need the one that's good for 11 fish at a time. So how do I do that?
4.15.
Yeah, the old one divided by
Square root of 11.
square root of 11. I like it. People put all kinds of weird stuff. This is n. This is not the mean. This is not, right? This is divided by square root of n. Okay. What do you guys get?
1.2513.
I like it. Everybody good with that? Yes?
When we're running down the probabilities for these scores, using this chart, should we always be saying approximately this percentage and stuff?
No. It's okay. Everybody else okay with this so far? Now some people will make this 1.25, look it up in the z-score chart. Is this a z-score? No, it is a standard deviation. So do you see what I keep saying? Label the formula you're doing at the moment. So you can go back and say, oh, it's just this. I haven't made a z-score yet. Because if you round it, it looks like a z-score. Oh, shit. You guys see what I'm saying? I'm trying to help you from the most common mistakes. Yes?
So now you do the formula.
Yeah, now, so this is that little extra step. Now I do every step I did over here. It's exactly the same work, but instead of 4.15, I'm going to put 1.251. That's the standard deviation that's good for this situation. So I can still draw the picture. Weehaw! Still put the mean in the middle, 18. I still want greater than 20. But now when I make the z-score, I use this. Because now everything is closer to the mean. Everything's less spread out.
Oh, it's not 11 with 18, is that?
No, definitely not. What does 11 have to do? What's 11? That's the number in my sample. What's the question about? X bar greater than 20. It's still the same data point I'm interested in, right? I like it.
0.0540.
You guys see what I'm saying? You would never put the number in there. We didn't put a 1 here, right? Even though it was one fish I was picking.
Because it's 0.9542 there.
So now, what do you get when you do this?
1.60.
Who is it? 1.60? Neato. And now you do the same work again. You look that up. It's going to be this area. I mean, do you see how all the work's exactly the same? You just have to first make a new standard deviation and then use it. But the work you do there is the same. It's just that all my data got closer to the mean, so there's less shit out here. So the answer here should be smaller. So here there was 31.56% out here. But now, if I take a sample of 11, everybody should get closer to the middle. There should be less stuff out here. So when you look at 1.60, what do you get? 0.9452. And so the actual answer is going to be 0.0548. So there used to be almost 32% out there in that tail. But now when I take 11 fish and graph those samples, everything moves to the center. There's less stuff out here. Now there's only like 5.5% out there. Yes, sir.
So is it not okay to use 1.59 or 1.6? Is it okay?
Oh, I don't know.
It'll give you a different answer.
It totally will. But what did it really round to?
So it's not 8.
Yeah, so 1.60 you got to use. Yeah. I like it. Again, I'm doing certain things just to get the ideas across. This is what this class is supposed to be about, is getting the ideas across. Once you get the idea down, you can start to worry about, well, technology would be a lot more precise. And I'm like, yeah, it sure would be, but it's not a great way to learn shit, to let the technology do all this stuff for you. But once you get out in the field and you got to do statistics, you're going to be using some kind of technology. I know that. But you got to know what the hell it means. The only way to do that is to make you do a lot of this stuff by hand and looking it up. Yes?
So trying to interpret this, basically the larger sample size you take, this will give you a more accurate depiction of what you're looking at. So
Well, yeah, of course.
Take random fish, you might see one bigger.
So guys, here's the idea. Let me go back to average age. I know I've used it a lot, but just as easy. There's an average age of Grossmont. If I take one random person, let's say the average age of Grossmont is 27. If I take one random person and they're 45 years old, would that freak you out? No. If you took a group of 30 people and their average was 45, would that freak you out? Yes, it should. You should go, wait, what? Where am I? What time am I? What? So if you randomly select from all Grossmont students 40, whatever I said, I can't remember. A certain group of people, 30 people, and their average age is that far off from the mean, that should freak you out. Why? Because if you take a group of people, their average should be even closer to the real mean. That's the whole idea of what a mean is. In fact, if I take the entire population as my sample, then it's going to be right on the mean, right? So then the standard deviation becomes 0. So as my sample size gets bigger and bigger and bigger, my spread gets smaller and smaller. The bigger my sample, the more certain I am about what I see, meaning the sample statistics should be closer to the real population statistics.
Just to clarify that further, so with the part B here, it's not saying you get a fish random, it's saying that the average of those
Yes.
11 fish.
If you took 11 fish, if you took a group of 11 fish,
Okay.
there's a 5.5% chance that their average length would be more than 20 centimeters. That's how to interpret this directly. If you went out and took a group of any 11 fish and randomly select 11 fish, there's only a 5.5% chance that the average of those 11 fish, the average would be more than 20 centimeters, which should make sense. The mean is 18. I expect 11 fish, if I take them at random, their mean should be close. It should be very unlikely that their mean would be that far away. It should be closer to 18, not above 20. Yes, ma'am.
I have a question, just to make sure, the x has to be larger than the number for you to do 1 minus the area?
Yeah, and I try not to, this is one place where you sort of could memorize it, but I try in general, don't memorize situations. Think about the idea. Whenever I use the chart, it tells me area below. The question wants the area above. So I have to do 1 minus, get the answer. So you could say anytime you see greater than, then you do 1 minus, but I kind of hate generalizations like that. Because you start to forget why that's true, and you just start doing it everywhere, and you might do it somewhere you really shouldn't. But what's the idea? Why does the idea make sense? The chart always tells me the area below. If I want the area above, then how do I adjust it? I take the whole thing minus that. 1 minus that gives me the other area. That's it. You're looking at me like, I still don't know, man. The whole thing is 1, right?
Yeah.
So that much is 95, roughly. Then that's got to be 5%. That's it. That's why 1 minus that gives me the other side. Yes. Hopeful. Okay, let me give you this handout. We'll talk about the one weird side.
My life away from it.
What?
So I'm giving my life away for it. Yeah. Yeah. That's good.
Wow, I want to live in New Zealand.
Holy moly. It's so cheap. I know where I'm moving.
All right, guys. So I tried to do a quick thing like this on the board. Not yesterday, no. The last day. But do you see how if I take and I put numbers in a hat, I think that's then it's a uniform distribution. Right? 1, 2, 3, 4, they're all equally likely to happen if I just take one out at random. So it starts off uniform. And then if I take samples of size 2, and look what I did. I did all the samples of size 2. Because that's really what this picture is. It's a picture of all the possible samples of size whatever. So to make one that you can see, I have to make it a relatively small group with a small selection. Do you see what I'm saying? How many samples of size 11 can I pick from all the... Holy shit. A lot. Way too many. So I kind of had to get it down just so we can see it. So I did this kind of thing the other day where I took all the samples and wrote them down. And next to it I put the means. So originally, what's my data? 1, 2, 3, 4. Now, once I take samples of size 2, what's my data? 1, 1.52, 2.5, 1.52, 2.53, all the means now. Those are what I'm going to graph. And that's what this is. This little histogram at the bottom. Does that look more normal than it did to begin with? Does the bottom one look more normal than the top one? Yes, because it starts low, goes high. It looks very normal, right? And the funny thing is, if you calculate the standard deviation of all these, you can just put it in the list 1 and do 1 var stats, right? You calculate this, the standard deviation, you get the original one divided by the square root of 2. It just happens. What's the formula to get the standard deviation for groups of size whatever? The old standard deviation divided by the square root of n. So if I take the standard deviation and divide it by square root of 2, I get the standard deviation for all these new data points, all the x bars. I love you guys. So if I put all the x bars into L1 and had the calculator spit out the standard deviation to me, it would be the original standard deviation divided by the square root of 2. That's what happens. Yes, sir? Where do I get the 2 from? Because how many am I picking at a time? 2. So n is 2. How big is the sample that I'm picking? How big of a sample am I picking for down here? How many numbers am I picking out at a time? How big is each sample I take? 2. If we were to select, in fact I say it, if we were to select samples of size 2. Okay. If I did samples of size 3, you can imagine this would get much bigger. But I could do all the same work and see the same kind of thing happen. Yes, ma'am. Let's do a couple things real quick. There you go. On the calculator. Man, today's an interesting day for me. Computer is not done.
I forgot mine, okay?
Maybe you need to borrow a calculator?
Yes.
Might want to do that.
My name is Jeff. What? My name is Jeff.
Make sure it turns on.
My name is Jeff.
Yeah.
22.0. This is right, correct?
Dude, I didn't even do it.
Oh my gosh, bro.
We're doing this.
Oh, watch out, you're about to step on my own.
Name is not Chuck.
Why isn't he talking?
All right, let's do a couple things.
Hey.
Go out there and see what that's about.
That'll be a bit.
All right, let me see. All right, first off, so guys, please, dear God, meet me somewhere in the middle here. Somebody turn off the one that says whiteboard, and then it says diagonally down. All right, guys. So the top here is, if I put 4 numbers in a hat, I pick one out, there's a 1/4 chance each one, right? 25%. Easy enough. They're all 25% height. Everybody cool with that? Mm-hmm. All right, now I take a number, put it back in, and take the next number. That's a little sample of size 2, right? With replacement, so none of my probabilities and stuff change. So what could I get? What samples could I get? Well, I could get a 1 and then a 1 again, as I put it back in, right? And so forth, so forth, so forth. Is everybody cool with that? This is all the samples that could happen. And now, what is this all about? What do I then, instead of plotting the individual things that can happen with the probabilities, I want to plot the group means with the probability. So now I'm going to look at these. These are my data points now. I think I did it. How many ones are there? 1. So see how that's 1 out of 16. How many 1.5s are there?
2.
See how it's 2 out of 16. Everybody with me?
Oh yeah. 3.
How many 1.5s are there?
2.
2 1.5s. 1 there and 1 there. Right? So what did I put down here? 2 out of 16. Plot it. Plot it, plot it. Somebody with me? Mm-hmm. All right, so this is the picture that I keep drawing. That's the new picture. That's the one that shows all the groups of size 2 at a time. And it definitely looks more normal. It's not quite normal, to be honest, yet. But it looks a lot more normal than it did. And now, what I want you to do, if you put, please do this, in your calculator in list 1. First off, double check me here. Put 1, 2, 3, 4 in your calculator first. And switch over. Make sure everybody remembers how to do this.
No.
So if I go to my list, stat, edit. Again, we're doing technology stuff, so dear God, let me know if something weird's happening in your lists or anything. Okay, no? Everybody's good? Now just put 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now let's figure out the average and the standard deviation. How do I do that? Stat. I don't want to sort it. Sorry, sort it. Calc. I want to calculate something. 1 bar stats, because I only put 1 variable. What's the variable? The number I pick out of the hat. That's the variable. So the number of variables is the number of lists. It defaults to list 1, so I hit enter. Then if you have the newer one, it says you can put L1 in there. Is everybody with me? So this is a population. Do you understand? This is the population of numbers in the hat. So what's my standard deviation? Yeah, 1.118. Please tell me that's the number I put down there. Thank gosh. Okay. Good job, Pass Jeff. Okay. So that is the original that's the standard deviation. That's how spread out the individual numbers are from their mean. Now I take samples of size 2, so that standard deviation won't apply anymore. It's different now. So if I go back and I put into my list, clear this one. Everybody do this with me. Just start putting in the X bars. So I would put 1, 1.5, 2, 2.5, 1.5, 2, and so forth. Everybody with me? See what I'm doing? Just putting in all the X bars. Not worrying about sorting them or anything. Just get them all in there. Should end up with 16 of them. Those are all the sample means, right? That's the new data. That's what I'm going to make a picture out of. My original data was 1, 2, 3, 4. My new data is samples of every size 2. That's the means of those. That's the new data. Now calculate its mean. Yes, ma'am. What it says dim mismatch. So you're trying to do 2-bar stats. Don't do that. Dim mismatch means you're trying to do 2 things at once, and the lists aren't the same size. I'm not sure what you're trying to do. Yeah, it's 1-bar stats. So go to stat, calc, 1-bar stats. If you have the newer calculator, you still tell it L1. If you did put it in L1, I don't know what you did. Enter. Now the standard deviation is what? 0.791. And sure enough, if I take the old standard deviation, 1.118, right, and divide it by the square root of 2, this should be the number that tells me how spread out size samples of 2 would be from each other. We just did it concretely. We just put all of them in there and figured out the standard deviation. Theoretically, it should be the individual standard deviation divided by the square root of 2. That's the theory. We just did it concretely. But if I do this, if I do the theory, bam! 7905. Why isn't it perfect after that? Because I rounded 1.118. That's the only reason. So that's the theory, is that, and then theory is, and people hear the word theory and they have completely wrong ideas about what the shit that means. In this case, it just means the theory is unconnected to a specific instance. Right? For any specific instance, that formula works. So if I could do all samples of size 11 fish from this pond and take all their averages and put them in list 1 and calculate the standard deviation, it would come out to be this, which is the original 1 divided by the square root of 11. So thank God I know this formula, so I don't actually have to go and do that every time. Oh, shit. So this was easy. Why? There were only 4 numbers in the hat. I was only taking 2 of them, so I can actually look at the whole thing. Here, if there's like 300 fish in the pond, how many groups of 11 fish can I take out of there? Oh my God. It'd be insane. We can actually calculate it. 300 choose 11. 300. Choose 11. There you go. Basically almost 4 followed by 19 zeros. That's how many samples of size 11 I could take if there were 300 fish in the pond total. You guys with me? So yeah, I can make a list of all of them. I can make a list of all the possible samples, list all the X bars, put it into, you probably couldn't use the calculator because I think it only goes up to 100. It doesn't quite make it up to 1 times 10 to the 19th. I don't know if you guys are with me. If I did calculate all those averages of all those possible size 11 groups and put them all in and calculate standard deviation, it'd be the same as what we figured out just by frickin' doing this instead. Which way do I rather do it? This way. Yes?
Why would that be combinations, not 38%?
Because you're not, you're not counting different orderings of fish differently from others. That's the difference in permitting. Because you already would have picked that group.
Got it.
Yes. Oh, thank you. Poor little dude. Oh, it's still going? That'll be a nifty part of this. I don't know. Just freaked us out. Hello, people. All right. Now again, this is my desperate attempt to get the idea understood. Even if you completely are like, I don't have a clue what the hell you said for the last 2 days, what actually happens in the work? Well, if you see me take a sample and ask about the sample mean, you change the standard deviation. That's the nuts and bolts of this. That's the practical effect of this idea. The idea is freaky as shit, maybe. But the actual thing that it does to you is this. It adds one line. Yes?
For the test tomorrow, are you going to give us a formula?
We're going to make a formula sheet as soon as we're done with this. So on the other side of the paper, you'll see some examples. Go ahead and try to do those. Oh, shit. You gotta know how to say shit in a lot of different languages.
Scheiße? What language is that?
Scheisse is German. Merde is French. I know how to say it in sign language. Oh, that's the explosive way. Yeah.
What is?
Yeah. But I just learned this.
Oh, yeah, that's...
Where you can also do that. That's the. So you got that flu or something. Let's stop talking about that. Can you guys?
Ew.
So do the problems in the back. If you want to group up with other people, feel free. Do these problems. I looked this data up. This is probably about 4 years ago. So if you're thinking about moving to Waikato, New Zealand, that's not the same prices. The San Diego one is from this last year.
Holy shit.